Okay, so the four major points, or the four major properties of the photoelectric effect is as are listed here. These, can I stress this for the exam? You need to know all four of these. Inside out, back to front. You need to know, you need to be able to write them down, because there'll probably be a question where it asks you to write them down. So, the first one is there exists a minimum frequency of radiation known as the threshold frequency, below which no emission can occur regardless of the intensity of the light. This is dependent on the metal. So you have a piece of metal, Josh and Wiley. You have a piece of metal. You have a light, and you can turn the frequency up on this light.
Yeah.
You start in like your radial waves and you get nothing. There's no electrons coming off. You turn it up, and now you're into like your reds. It's still got nothing. And you get past green and suddenly electrons start coming off.
Yeah.
That green, whatever frequency it happens to be, would be a minimum threshold frequency.
Yeah.
You also have another dial on your light that increases the intensity. You make it brighter. You take it back to red. And you make it as bright as the sun, but it's just emitting red light. What happens? Nothing. Absolutely nothing. You turn it up to green. What happens? Lots of electrons come off. As soon as you hit that threshold frequency, the electrons come off, but it has nothing to do with the intensity. You turn the intensity all the way down, you put it down to there's one photon coming out per second. And it's set to green, so very low intensity, but set to green. What happens every second? One photon comes out. What happens when it hits the plate? One electron. Assuming it interacts, which is not always the case. Sometimes it will go through. Remember how there's empty space in atoms and between electrons and atoms and stuff? Sometimes it will just go through. But in theory, at least, it would hit an electron every time. So you get an electron coming off. One electron per second. That's number one. Number two. We go back to what we've got here. We've got our thing set up. What's above green? Roy, G, Viv. B, I, V. So that's blue, indigo, violet. I turn it up to indigo. What happens? More electrons come out? More electrons come out, do you think? Or just that it keeps letting electrons out? More comes out, yes, that's right.
Yeah,
Because you remember that picture we had with the gap?
There's green's the minimum.
So that remember there was that 4.7, that's where the most energetic electrons are, and there was stuff below that.
Yeah.
That green corresponds to that minimum gap there.
Yeah.
Now you're in violet, you can get stuff that's below that, so you can get like 8, negative 8, and that will jump up as well. You turn it up higher frequencies, you get more and more electrons coming off until you get the ones that are like tightly bound by the nucleus. They'll come off, and eventually there'll be no electrons left, and then what do you have? A whole lot of electrons. What is something? It's a gas without electrons. So there's four. Do you remember that there are 4 states of matter?
Yeah.
Solid, liquid, gas, and what's the last one? Plasma. We've got no electrons, and it's a gas. It's a plasma. So yeah, that's that last one. That's number 2 there. So radiation above the frequency will cause electrons to come off, regardless of the intensity.
Yeah.
Number 3. Photoelectric current is independent of the frequency of the radiation, so long as it is bigger than the minimum. So in this one, so we've got it on green, we turn up the intensity, which would be that way. We turn up the intensity. As we turn it up, how many more electrons are coming off every time? Lots. So every time we turn the intensity up a bit, we get more electrons coming off, so long as it's at green. And the very last one, electrons are given off with a range of kinetic energies ranging from... So to go back to what we were saying just before, you don't get more electrons when you turn it up to violet or indigo or whatever. So disregard what I just said. But they do have more energy.
Yes, you get more energy.
So they're given off with a range of kinetic energies between 0 and an absolute maximum. And the maximum is dependent on the frequency.
Yeah.
And this is a linear relation, and it's dependent on the frequency of the radiation, providing that it's larger than the minimum you require. Okay, we're getting up to this dude.
How old was he in
30 something? Not hugely old. This is Einstein in 1905. 1905 was his miracle year. He did so much work in that year. It's amazing that one human being could do that much work in 1 year. Possibly. No, it wasn't invented yet. So he was able to develop an explanation for the photoelectric effect that didn't use electromagnetic waves, that instead considered a stream of photons. Question number 1. What did Einstein get the Nobel Prize for? No.
No, it was
invention?
No.
Longevity?
No. Einstein got the Nobel Prize for the discovery of an explanation for the photoelectric effect. He got it for this. He did some other really awesome stuff, but at his time, they couldn't prove it fully. In fact, we've only really just got to that point now. So they didn't want to rush and give him a Nobel Prize with the possibility of it being wrong. We are not medicine. I say that because medicine gave a Nobel Prize to the person who discovered the frontal lobotomy as a cure for depression. Do you know what a frontal lobotomy is? Rosie? Is it something to do with... No, not quite, but it's sort of that level of quackery. No, not their eyes. They actually take some of the frontal lobe out.
They take out
Yeah, it works fine. It's just you end up like a vegetable. Well, not really a vegetable. You're alive. You've got no emotions. So you just sort of walk around like... They gave that person the Nobel Prize for chopping up people's brains.
But wouldn't they like walk around like brain dead basically?
Yeah.
You going down basically.
No, well, most of these people stayed in institutions their entire lives. So they weren't... It's...
contribution to society.
Yeah, it's a terrible thing to do to the human brain. It was also really dangerous. More people died than survived.
Yeah.
So physics, we are very cautious people. We've been pretty sure on like gravitational waves for a really long time now, but we only directly observed them last year. So we were only Like, yeah, they exist last year.
Yeah, because they had that really long. What was that? Is it on that really long tube? What was that?
No, that's not to do with. That's to do with the Higgs boson, which is another thing we were being very cautious about. Okay, that was the first question. So Einstein received his Nobel Prize for the photoelectric effect. Question number 2 is slightly easier. What country did Einstein come from? Germany. Question number 3. What religion was Einstein born into? No. No. That's you're confusing political ideology with religion, Wiley.
Jew.
He was a Jew.
Was he?
Yes.
Oh.
Now, worth noting, not a practicing Jew, but he was a Jew.
What?
Question number, what are we up to? 4?
Yeah.
What time was he living in Germany?
During that time.
During the Nazi period. Question number 5, what happened?
It was like when they took over Germany. No, he fled. Didn't
Yes, he fled and applied for asylum in America.
he? Yeah, and then that's when they used him.
And that's when he did some of his work. He also was helpful in... he sort of suggested that they make the atomic bomb, but he was not actually involved in the work of it. No.
He kind of just gave him a push in the right direction.
From those 5 points,
Is that when you went into like
no, not really. It was they were trying to end the war.
This was near the end.
Yeah. So to come full circle on that one, Einstein was a refugee. If America hadn't taken him in, he would have died in a concentration camp.
Yeah.
I just want you to take that home, to think about that. That Albert Einstein was a refugee because he was a Jew.
Yeah.
So just keep that one in mind. Particularly when people are like, oh, well, we should round up all the refugees and send them to Germany or something like that.
What year was that? That was like
I think he fled in 32, so it wasn't even the height of the Nazi regime yet. But it was getting there.
was that like after he'd done
It was after he'd done this, but general relativity didn't come until after he got to America.
So if he had died there, what
We basically... stuff that you wouldn't understand. Lots of theoretical physics stuff we wouldn't have today. Or we might have, someone else might have discovered it, but it may have taken longer. Yeah, the other thing is that the war probably would have gone on for longer because he wouldn't have been around to suggest that maybe we could use this thing as a
Yeah, well,
weapon.
It might not be that. The Germans might end up having it first before us.
Yeah, that's true.
They were the-
Hitler saw nuclear sciences as a Jewish pursuit
Yeah.
and outlawed the research of it. The Nazis were actually quite close to the atomic bomb themselves.
They were. Except for the dude that was leading his science labs
Yeah.
and became really happy.
Yeah. Look, I just think everyone should know that how important Einstein is, and the fact is that we may have, like, if history went a different way, if America wasn't like, hey, yeah, come here, you, we may have lost it. We may have had someone who had an immense contribution to science die in a concentration camp. It's just worth thinking about.
He has a pretty good staff, though.
Hmm?
Staff.
Yeah, he's a... Alright, so Einstein... One more thing, actually, it's not related to the original 5. One more thing. Einstein's hair was genetically predisposed to be messy. As in, his hair, he could comb it, and it would go back to buffy, messy hair. It is a very rare genetic disorder. It is a very minor genetic disorder as well. But his hair would always go buffy.
That's why it looks crazy.
Yeah.
Might have been a while ago. He could cut and yeah, it's super.
He also Not the cleanest person in the world. Wore the same jacket for like years on end and stuff like that. Yeah. Yeah, it was a nice leather jacket. So.
Yeah, wasn't he? Was it dyslexic or something as well?
No, probably not. He never finished school though.
That's
Yeah. Yeah, well, Einstein's fascinating, absolutely fascinating man. Anyway, let us get on to his contribution to physics, because I feel like I have filibustered for a while. Okay.
Isn't that the next?
Have you ever heard that?
I only use that when my neck thought still part during this practical filibuster.
Yeah. And I'll be like, you don't know what this means. So Einstein made, and you have to be able to remember these, he made the following assumptions to explain the photoelectric effect. You have to remember his assumptions. So you have to remember the 4 major points about the photoelectric effect. You have to remember Einstein's postulates, which is this stuff. And then you have to remember how they fit together. So he assumed when light is emitted, it is not emitted in a continuous way, but in discrete bundles of energy. I.e., they are emitted as photons, Josh Wiley.
Yeah,
Like
like
in the last
I'm
time we
reading
had 2
this.
more Joshes.
This built on, he didn't come up with this out of thin air. It built on someone else's work. As Newton said, I have only seen so far because I have stood on the shoulder of giants. All great science builds on what comes from before it. So this built on Planck's work from 5 years beforehand. So Einstein and Planck were like this. They were best buds. Actually, I don't think they were. I think they argued all the time. But their work was synonymous, like sort of together. Almost collaborative, yeah. The intensity of radiation is proportional to the number of photons crossing a unit area per unit time. That is, more photons going past the point, the higher intensity. So I've got a laser with a very, very small opening. I shine it at the wall. It doesn't appear very bright. I open the opening a little bit more. More photons are going through. It appears brighter. Keep opening it, it gets brighter and brighter and brighter. Because there are more photons. I increase the photons that come out in the beam, and it gets a higher intensity as well. Okay. Yes, like a slit in the curtain compared to opening the curtain. Or a dimmer switch. Okay. When a photon collides with an electron, it may, not definitely has to, it may transfer its energy to the electron. Such transfer of energy is instantaneous. It happens straight away. It's like if I throw a tennis ball at you and it hits your head. The collision happens instantaneously. It doesn't happen over like an hour. The energy goes into your head and the ball bounces off instantaneously. If this transfer occurs, the photon must give up all of its energy or none of its energy. It can't give up some of its energy. All of it or none of it, and instantaneously. But it can happen or it can't happen. It doesn't have to happen. Okay, so let us use that to consider the 4 points from before. So consider copper again. And let's see how Einstein's assumptions line up with what we know about the photoelectric effect. This is, if you can't remember the stuff from before, remember this. Okay, because this ties it all together. Note that the energy level diagrams that we've been using depict it as an energy level, but it's not an actual depth. So an electron with a energy level of -8 could be exactly the same point as 4.7. They could be at the same level, like they could be sitting on the surface of this desk right now. They don't have to be deeper than. Okay? They're in that sea of electrons. Okay, so if a photon collides with an electron, it may transfer all of its energy. If the energy of the photon is less than the band gap, remember the band gap between 0 and 4.7, no electrons could be there. If it's less than that, what happens? What would happen if the electron got the energy from the photon? Say it got 1 electron volt and it was at 4.7. What would happen to it? It would jump up and go down. The electron knows that it can't do that, so it won't take that energy. It's a little bit more complicated than that, and it has nothing to do with knowing what's going on. But it won't take that energy. So it is less than the band gap, then it won't take the energy the photon carries on in its merry way. Thus, there is a minimum frequency below which no emission will occur, because if you've got an energy lower than that 4.7, the electron can't pick up that energy, so it can't escape. This is just an example here. The minimum energy for copper, the minimum frequency for copper is 1.13 times 10 to the 15 hertz, using the equation from before and some values. If you would like, if you want me to, I can go through that in greater depth, but I won't do it in the lecture notes. Notice that the threshold frequency is calculated from the work function of the metal, which is that 4.7 bit. That is the gap. So the work function, if it has a higher work function, it becomes like 8. Lesser work function becomes like 2. That's the work function there. This is different in every conductor. If we increase the intensity, we only increase how many photons reach the surface, not their energies. Number 2. All photons greater than 4.7 eV in copper may transfer their energy, and they're transferring all of their energy to the electrons when they collide. This will happen instantaneously, and the electron is emitted without delay. Photon in, electron out, straight away. It does not matter how intense the radiation is, and 1 photon can be enough to cause emission. Number 3, if we increase the intensity of photons, we are just increasing the number of photons falling on the surface, hence no amount of intensity, no brighter light, will cause the emission of the frequency if the frequency is not enough. Increasing the intensity only increases the current that you have. So very little intensity, very low current, higher intensity, higher current, assuming we're at the right frequency. And number 4, consider a photon of energy 10 electron volts. What's it going to do to the most energetic electron? It's going to be 10 take 4.7, so it's going to give it 5.3 electron volts of energy. So that photon now has 5.3 electron volts of energy whizzing around the room. What if the electron that it hits was at 10 electron volts? It will jump the gap, but it will just sit there at the surface. It will have 0 electron volts. What's the minimum? That one there. The one that's had 10. Puts it exactly on the surface. The maximum, what was that, sorry? If it's any less, it won't take it. If it's any less, then it would end up in the band gap, which is a no-no. So it goes between 0 and a maximum. Cool, there you are. Einstein, done. You just got your PhD. If you travel back in time to 1901 or whatever, you can sit down and you can write your own. You can write your own Nobel Prize certificate. By the way, he didn't get the Nobel Prize in 1905. It was for his work in 1905. I think he got it in 23 or something like that.
That's it.
Yeah.
Sit back and go, I was modeling maybe physicist from
If you took me to 1900, yeah, I'd probably say that. But the 60s, no, I wouldn't be smarter than most of the physicists there. And I guess the difference is I know a lot of this stuff because I have learnt it from them. Yeah, I've stood on their shoulders. So, cool. The maximum kinetic energy of the incident photons minus the work function. Sorry, the maximum kinetic energy of the electrons is the kinetic energy of the photons minus the work function. So that is Kmax is hf take W. So the questions you'll be doing for this topic will give you the work function, they'll give you the frequency, and they'll ask you to find the maximum kinetic energy. Work out like that. Graphing this gives us a linear relationship. And it will give us a Planck's constant as the slope, which we'll be doing. Okay, cool. X-rays, awesome. Okay, so in 1895, Wilhelm Röntgen, discovered that electrons with high speed create some form of invisible radiation, and he called them X-rays. And unfortunately, we never came up with a better name for it. I'm sure that he was expecting someone to come up with a better name, and they didn't. The unknown ray, but that just never came up with a better name. He demonstrated that these were very, very high frequency, higher frequency than light, higher frequency than ultraviolet, and that were the only ones we knew at the time. And that they could penetrate where light could not. X-rays were used within weeks to help set a broken bone. Beforehand, it's hit and miss. You break a bone, sometimes they'll set it properly, and your arm will go back to normal. And other times they'll set it not right, and you end up permanently deformed. Let's break it again. Yeah, of course, that's always a possibility. Do you remember when we went to University of Adelaide together?
Yeah.
And we went to the science labs? That weird dude, yeah. We went to the building called the Braggs. Do you remember doing that?
Yeah.
So William and Lawrence Braggs, and I think I've got their first names right, Bragg, got the Nobel Prize, and it was to do with this sort of thing. To do with running X-rays on broken bones. So basically, they were like, yeah, cool, X-rays, we've got it. Let's use them to fix broken bones and stuff like that within a couple of weeks. People were like, yeah, let's use this thing. Unfortunately, didn't realize that they, can kill you. They used to use them to help pick your foot size. You used to stand on a grid that would shoot X-rays up at you to work out what size your shoes should be. Really good at deciding what size your shoes should be. Really good at killing you. So there are a whole lot of people with stubs instead of feet because they had to have their feet removed because of these X-ray things. So
Is that so much cancer?
yeah. So really great discovery, but maybe they should have just held off for a couple of more weeks. Of course, the Curies and all that sort of stuff was when they discovered that this stuff was harmful.
How long did it take before they
Realise it was
The exposure to the right level of X-rays can kill you straight away. I don't think that was what was happening because I don't think they could produce that many straight away. But we're probably talking months, and they started getting sick and dying. Yeah, why is everyone dying around us? I don't think it has anything to do with getting shoes. That's for sure. It turned buying shoes into a lethal pursuit.
Hey.
Hi, Ken. So X-rays are produced when electrons are accelerated by voltages of between 10,000 and 200,000 volts. It's a lot of energy. Remember when we had the electron deflection thing set up, that was like 9,000 volts. So if we had it going any faster and it was hitting the right target, it would be producing X-rays. When they strike a targeted anode, the energy is converted into mostly heat, but some of it's converted into very high frequency radiation. So this is not the photoelectric effect. What happens is the electron comes in, it slows down almost instantly, and the energy is released as a photon. It's sort of like the reverse, but not really. X-rays have a wavelength order of magnitude between 10 to the negative 9 to 10 to the negative 11. Cam, if you want to talk to someone, we're going to be recording till the bell goes, so sorry about it.
When did I start to see actually?
Week 3.
What that?
Wednesday?
Cheat sheet, you say?
Oh, good.
And need to speak.
Well done, Cam. We're proud of you. That's why you came in here.
No, I just don't really do anything.
So this is sort of a very simple version of what an X-ray device looks like. So we have a very, very high potential difference between the anode and the cathode, and the electron comes off the filament, like what we had with the electron deflection tube. It flakes off, but then it's caught in a really, really high voltage, and it's accelerating. So if it's an electron here, what side is this going to be? Plus or minus? It's going to be plus. We don't want it to be pushed away from it. We want it to be brought over. So plus. It's going to fly over. It's going to hit this bit here, and that's a heavy metal, and that is going to let out an X-ray. This can be various things. I think I've got a list of what they are in here somewhere, but I'm not sure. The anode, which is commonly made of copper. There we are. It's designed to be a very good conductor of heat, therefore most of the heat is so that's the part around the outside of the target. It's designed to be getting most of the heat away from the target straight away. Why? Because otherwise your device will break really quickly, as opposed to sort of quickly like it's going to. The system is cooled, so you've been in for an X-ray and you've noticed they're really, really cold in there. Have you noticed that before? It's because they are cooling these things like as much as they can, because they do break down really quickly if they don't get cooled. The surface that it's hitting is most commonly tungsten, which is relatively rare, and that's where the electrons actually strike. Cool. So the spectrum of X-rays is emitted with a continuous range of frequencies up to a maximum, which is what we'd expect. The electrons can have all the energy from the gap, or they can have some of the energy, or they can have no energy. All of the energy will be this maximum point, and then there'd be a minimum point. It's the maximum is directly proportional to the voltage of the X-ray tube. The voltage increases the X-rays that are emitted. Continuous radiation is this part here, the curvy bit, that's known as Bremsstrahlung or braking radiation. Bremsstrahlung. There's also these other points, these peaks, which we talk about next. They're known as characteristic X-rays, and they vary between different metals, and you don't get them at low voltages, you get them at higher voltages. For example, tungsten, you need 72,800 volts to get them. However, I could give you a whole series of metals in X-ray devices. You could detect these characteristic X-rays, and you could use them to determine what metal you had. Just cool. And these don't move. So if you increase the frequency or you increase the intensity, they don't change where they are. They're still in the same spot. Hence characteristic X-ray. Probably not, no. They probably never turn those devices up to that level. When electrons enter the anode target, they encounter mostly empty space. It's what we'd expect, because there's the nucleus and there's the electrons miles and miles and miles away. Not really miles away, but a long way away. They can either hit the nucleus, be slowed down by it, or pass through without interacting at all. Due to Maxwell's work, remember Maxwell from ages ago, we know that accelerating charges emit electromagnetic radiation. How can we accelerate? What type of acceleration are there? There's speeding up. What's the other one? Slowing down. If I'm an electron and I hit a target, what am I doing? Slowing down. I'm accelerating. If I'm a charge and I'm accelerating, even if it's a negative acceleration, what's happening? I'm emitting a electromagnetic wave. But with enough energy, what I'm emitting is X-rays. As the electron can lose energy on a spectrum between all or none, it's outputted on a continuous between 2 points. The energy of, this is similar to what we've had before, the energy of emitted photons is dependent only on the energy of the electrons, hence Emax is, so that's the energy from the voltage. HF, E equals HF is another equation, which equals that. So we get HF equals that, and we rearrange and we get the frequency. The maximum frequency is E delta V over H. 2 constants, 1 not constant. So changing the voltage is the only thing that changes the energy, the frequency of the X-rays. I don't know if you've noticed, but I'm trying to rush through this. Sorry guys. Don't worry, you can ask me questions next week. Yeah. I would recommend that you read through all of these notes again and you read the textbook. I know I say that every week, but this is the topic that you most need to read. Maybe go home and watch some YouTube videos as well. Okay, so what is light? What have we discovered so far about the nature of light? Wiley, what is light? Is it a photon or is it a wave?
It's negative.
Hands up for photon.
It's negative.
Hands up for wave. Hands up for Wiley's suggestion, which was neither. Yeah, it's neither. It's both. It acts like both. Josh, keyword, acts like, keywords. It acts like both, but it is neither. There's no simple answer, basically, is to that question. As we get to the higher frequencies, it acts more like a particle. As we get to the lower frequencies, it acts more like a wave. No one at this point, right now, has ever observed a radio wave acting like a particle. At this point, no one has ever observed a cosmic ray or a gamma ray acting like a wave. Maybe one day, yes. It might be very difficult to do. Yeah, so it's possible, however, very difficult to see the wave properties of X-rays. It's mainly because it's very difficult to get the slit small enough in order to get it to diffract. We use crystal atoms in a lattice because they're very, very, very close together, and we'll get X-rays diffracting. Any waves with frequencies smaller than that are impossible to observe because we obviously can't get the space is smaller. We also, have a real trouble getting radio waves to act like particles. Okay, uses of X-rays in medicine. Cool. I think there's like 2 pages on this, hopefully. Okay, so they were using X-rays to scan people's feet. X-rays pass through matter with varying degrees of success. And they also react with photographic plates. Therefore, we can use X-rays to image parts of our body with varying degrees of success. They're produced by placing the body part over a plate and shining X-rays down. X-rays pass through different parts of your body better than others. This flabby stuff, they pass through real easy. This stuff, they pass through real easy. The muscle, they pass through reasonably easy. Bones, they have a lot more trouble with. Because your bones absorb X-rays. You can observe muscle damage with an X-ray. We don't really do it much anymore. We used to do it a lot. We don't do it anymore because we've got MRIs and we've got other different things that can do them. So our bodies absorb different amounts, and hence we get an image. They're called magnetic resonance imaging. So they use magnets. It's pretty clever stuff. Antimatter. PET scans. So the degree. CAT scan is just an X-ray. The degree of exposure on the photograph, guys. The degree of exposure on a photographic plate depends on the degree of absorption. So, what it's shining through, how much it absorbs, the penetrating power, how powerful the X-rays are, and the time that it takes. We try to limit the time that it takes and limit the hardness of the X-ray depending on what we are photographing. So different X-rays have different exposures to stop you from dying. Attenuation of body tissues depends on these factors. It's the density of the tissue, so some skin, or skin is rather not dense, muscle is denser, bone is very dense. The thickness, how thick it is, so through my end of my pinky, it's pretty thin, through like straight through there, it's quite thick. And the atomic number of the elements used to make up the tissue. So if I had lead in me, for example, then it's got higher attenuating power. Areas with higher attenuation develop white, and with lower attenuation develop black on the plate. White means no exposure, black means full exposure on those X-ray things that you've got.
That's just where it's
Yeah.
well,
So you put your arm on an X-ray plate.
everything is
Around the outside is white, and then right way around.
the outside's
Black.
on
The outside's black, then various shades of white.
Yeah. Well, the out should be bone usually shows like white, and the outside layer is skin.
Yeah.
So that shows up.
For the plate to expose, the X-rays must pass through the tissues to be photographed. Obviously, if you're in the other room, the X-ray doesn't work. If you set it up and the person's in the waiting room, please, and you press the button, you don't get an X-ray, surprisingly enough. The greater the energy of the photons, the further it's able to travel through matter. Hard X-rays are produced with a voltage of 100 to 150 kilovolts, and soft X-rays are produced with a voltage in the order of 50 kilovolts. And we use different hardness of X-rays depending on what we're scanning. Prolonged exposure to X-rays can be harmful, believe it or not. If you didn't get that from me saying that you will die. So the time at which the patient is exposed to radiation is limited where possible. They weigh up the risks. They might have to give you a 10-second exposure to X-rays, but they might be able to stop you from dying of bonitis, I guess. So they weigh it up. Determining the appropriate hardness that they need to use, and determining the intensity that they need. An X-ray tube has two settings. You can change the voltage and you can change the current to give you various different outputs. Thank Christ for that.
So,
Okay, that is the end of that.